This conference will now be recorded.
Hello everyone. Today we will discuss radioactive reactions and different types of radioactivity, and then we will discuss the problems. Okay. First, we have to know some terms that we will use in radioactive reactions frequently. Okay, that is some particles, and then what is their symbol, charge, and mass. Electron, proton, and neutron. These three are the subatomic particles, and these are their symbols: E minus, P plus, because proton is having positive charge, electron is having negative charge. The amount of charge is -1, this is +1, and for neutron it is neutral and there is no charge. And if we consider mass, the mass of proton and neutron are same, but mass of electron with respect to proton and neutron, this is very small, that is 1/1840 times of proton and neutron's mass. So this is very small value of mass for electron. Now atoms are made of proton, neutrons, and electrons, and if we consider atom, then in the nucleus there is presence of neutron and proton. So neutron and proton, they will be in the nucleus, and electrons, that will be present outside. Okay. Now, what is the basic difference between radioactive reactions and chemical reactions? Chemical reactions, it will involve only electron. But when we are talking about radioactive reactions, it is basically the reaction of the nucleus. So that is the difference. Electron and proton, these two together actually influences the chemical properties. But when it is protons and neutron number, that is no electron we are involving, in that case it will influence physical properties. Okay. So if there is same number of electron but difference in the number of proton and neutron, physical properties will be different. So radioactivity, it is actually the process of spontaneous disintegration of the nuclei of heavy elements. Now, in which case radioactive reactions are possible? Remember, it is for heavy elements. Okay, not the usual elements that we involve in case of chemical reactions. So it is only for heavy elements, and in this type of reaction there is also emission of certain types of radiation. Okay, so disintegration, that is there will be some decay of the nuclei. Nuclei means where neutron and protons are present. Now depending on what type of radiations are emitted, this emitted radiation from unstable nuclei, they are actually alpha, beta, and gamma ray, and together we can call them as ionizing radiations. Now these radiations, they are not influenced by outside conditions such as temperature and pressure. So normal chemical reactions, what we see, we can change the reaction condition, that is temperature you can change pressure, and also there is direct influence on the reaction mechanism or product type. But when we are talking about radioactive reactions, then temperature, pressure, all these things, now it will have no value. Okay, so even if we change it, there is no direct influence. So all radioactive reactions follow first order kinetics, and that is the reason we are discussing here these radioactive reactions under chemical kinetics chapter. Otherwise this is a completely different chapter, that is nuclear reactions or radioactive reactions. Okay, but as the mechanism, that is the rate expression that you will see, it is just like first order reaction. Okay, so that is the reason we are discussing it. But remember, there are some dissimilarities also present. It is not that all the criteria for these radioactive reactions and first order kinetics are same. No, it is only the kinetics that are same, but there is some other dissimilarities. Fine. Now when we will that is in case of radioactive reactions, there is certain notation that we will use. There is a specific way you have to write them. So see here we have written 16 oxygen 8. Basically it is like this, 16 oxygen, and in the suffix it is 8. Now what it means? It means this is the number of protons. So there is 8 proton, P plus, and here it is mass. Now mass is basically total number of neutron plus proton. You know what is the number of proton, and total mass is 16. That means 16 minus 8. That will give you the number of neutron, 8 and 8 both. And remember, always the number of proton and electron, both these are always same, because ultimately the charge should be balanced, because atom is neutral. Okay, so if there is 8 proton, there must be 8 electrons. Okay, similarly next is 31 phosphorus 15. So this is the number of proton, obviously number of electron, that is also 15. And how we will get the number of neutron? It is 31 minus 15. 16 neutrons are present. And the last example, 65Zn30. This number will give you, that is a number which is in the suffix, it will directly give you, that is subscript. So okay, this number will directly give you the number of protons, that is atomic number. And as atomic number is 30, total number of electron, that will also be 30. And number of neutron, that you can get by subtracting number of protons from this mass number. So this will be equal to 35. So number of neutrons will be 35. So whenever there is this type of expression, that is any element X and this subscript and superscript, you will be easily understand what will be the number or mass number and atomic number. So here Z is atomic number, A is the mass. Okay, any doubt? So in this way we have to express different atoms. And the significance of this type of representation is directly you can understand what is the number of protons, neutrons as well as electrons. We will see some particular statement which are related to radioactive reactions. We measure the rate of reaction in chemical kinetics based on rate of change of concentration of reactant or product. So that we have already seen, that in case of normal chemical reactions, how we express the rate of reaction. It is either by the rate of change of concentration of starting material or the formation of product. But this method, it is not possible in case of radioactive reactions. So it will not work for calculating the rate of radioactive reactions, because most of the time radioactive substance, that is when the reaction is going on, it is present in solid state. Normal chemical reactions, what we see, we take some solution. Okay, so we express the concentration in that is moles per liter like this. But this you cannot do here, because there is no such solution. They are present in solid state, so no question of expressing concentration of these species, that is starting materials. So what we will do here, we follow some different method. Its concentration would be constant with time, because when it is solid, we consider their concentration as 1. Okay, that is the rule we follow, assuming it to be pure and that the product does not remain with the reactants. That means when you are considering the reactant, we can assume that there is no trace of product. It is purely only the starting material. Okay, so how we will measure it if it is not possible by the normal convention? The rate of radioactive reactions are measured by calculating rate of change of nuclei. That is, we are talking about nucleus. Nuclei means the particles that are present in the nucleus, that is proton, neutron. So rate of change of in the number of nuclei of the radioactive substance. In this way we express the rate of radioactive reactions. That is, radioactivity we can express in this way. Now some terms we have to know: activity and specific activity. Sometimes it is also called radioactivity. Both are actually same. So what is radioactivity or activity? It is based on counting of disintegration per second. Okay, disintegration means there will be change of the nucleus. That is the disintegration, and it is expressed as disintegration per second, DPS, disintegration per second, okay, DPS. And when it is specific activity, what is the difference between activity and specific activity? Now the activity is per unit quantity of radionuclide. That means it will be per gram or per kilogram. That is per unit mass, per unit quantity. So specific activity will be defined as the activity per quantity of atoms of a particular radionuclide. And the unit that we use for specific activity is BQ. BQ is basically becquerel. Becquerel per gram or curie per gram. Now these two units we have not discussed it yet, but we will discuss it in the next slide. Okay. But remember, it is just like activity, but only difference is now it is per unit mass. It may be gram. Here only gram is mentioned, but it may be kilogram also. That is BQ per kg or curie per kg. Now we will see what is the relationship of BQCI, that is curie, with DPS, that is disintegration per second. So all these are basically different names of the units by which we can express radioactivity. Here we have all the units. Becquerel, that is BQ. So becquerel is basically SI unit of radioactivity. Okay. And 1 BQ is 1 DPS. So these two are basically same. So when we are saying BQ per gram, it is exactly same as DPS per gram. And curie is non-SI unit of radioactivity. And see, 1 curie, it is having a very large value. So 3.7 into 10 to the power 10 DPS, that is equal to 1 CI. That is 1 curie. Okay. So remember, these are the relationship between CI and DPS. Mostly BQ is not so much used. These two units, their use is very frequent. Okay. Next, we'll see that how we can do the integration. Similar type of integration you will see here that we have done for first order reaction. That is for normal chemical reactions during the discussion of first order kinetics. The way we have done the integration, here also we will do the same. So suppose there is a radioactive decay starting from A and we are getting B. Rate of reaction, or better we say, mostly in radioactive reactions we use the term disintegration rather than rate of reaction. Mostly these two are same. Minus DND. So what is capital N? Capital N is the number of nuclei of A species. Okay. And minus DNDT, that is the rate of change of in the number of nuclei of A. Obviously, with time, the number of A nuclei which will decrease. That is why there is a negative sign. So minus dN by dt, rate of change in the number of nuclei of A, that is directly proportional to this number capital N. So this proportionality sign, if you are removing, you have to place a constant. And this lambda is basically, sometimes it can also be expressed as K. This is rate constant. Okay. Now what we'll do, we will bring this N term in the denominator left hand side and dt we will bring in the right hand side. Okay, because we have to do integration. So N naught, that is the number of nuclei of A at time 0. That means initially the number of nuclei of A is N naught, and when it is time t, then the number is capital N. Now rearranging this, now see how we have written it, dN by N and minus lambda dt. We will integrate it, and what are the limits? Limits are N naught to N, 0 to T. So when you do that integration on dN by N, it will become ln N. Now ln N, the limits are N naught N. So that is why ultimately it will be ln N minus ln n naught. And in the right hand side, it is simply integration of dt, so it will be simply t. Now finally what we are getting, as it is ln minus ln naught, you can express it in this way, ln n by n naught, that is equal to minus lambda t. Okay, now in ln, base is e, so if you want to remove the ln term, then what we will do, n divided by n naught, that will be equal to e to the power minus lambda t. Now in the left hand side, okay, it is minus, yes. Now you can shift this n naught to the right hand side, and ultimately the expression will be this. See, this is same as this, n equal to n naught, and this type of expression we have also seen in case of first order reaction. Remember how we have expressed it. We have expressed it like this, a naught. So this third bracket I am using here, which is for concentration, minus lambda t. Just compare these two expressions. These two are almost similar. Only, sorry, we use k here, not lambda. That is normal chemical reactions, we use k, but in radioactive reactions, though k is also used, but lambda can also be used. So these two expressions, you can see this is totally analog to each other. So that is why we say that radioactive reactions, they follow first order kinetics, okay, which is clear from this expression. So is there any doubt? Now we will see types of radioactive decay. Though here details are not required, but why I am discussing this, because sometimes when you will get numericals, these different types of terms can be mentioned, so that you are not confused. So that is why you should know it, what is these different types of radioactive reactions. So when we are saying that it is alpha decay, alpha particle is basically helium nucleus, that is He, atomic number is 2, mass number is 4. Here our starting species is Az. So remember, A means mass number, Z is atomic number. Now when helium particle is removed, that means helium is removed. So now 4, A minus 4 will be the mass, because now mass is reduced from A to A minus 4, because helium particle is removed. And atomic number, that will decrease by 2. So A is decreased by 4, Z is decreased by 2. Okay. So see here, this is X and helium is removed. Okay. And see here, in helium we have 2 neutron and 2 proton. That is clear from the picture. Fine. Because when it is 4 to helium, here 2 is the number of proton. That is P is 2 and N is 4 minus 2, which is also 2. That means both are 2. So this is actually helium 4 2. It is removed and we are getting Y. So this is a newly generated species. Next process is number 1, beta decay. Now beta decay is nothing but removal of electron. So when we are removing one electron, we know that mass of electron, we generally ignore this because the value is very small. So that is why here mass of E is 0, but charge is -1. So when -1 is removed, basically the atomic number of Y, now it will be Z plus 1. So here Z will increase by 1, but A will remain unchanged. Okay. And if you are not, that is having any trouble to understand how we are writing this at new atomic number, this is very easy. When you add these two numbers, you should get the number which is present in the left hand side. So if you add -1 plus Z plus 1, what you get? You get Z. So when you are adding these two, you should get the number which is present in the left hand side. Similarly, if you add 2 and Z minus 2, you get simply Z 2 will be cancelled. Similarly, if we add the mass, so here mass is 0 and A. So 0 plus A, that is also A. So left hand side we have mass A. Okay, so this is basically removal of electron, that is beta decay is nothing but removal of electron. So this is the electron. Fine. Next is gamma decay. Now all these are different names of radiations, alpha, beta, gamma. So when gamma is emitted, there is no atomic number, no mass. It is simply 0, 0. That means A and Z both will remain unchanged. And this is a radiation, that is why this type of sign is used. Fine. Number 4th method, positron emission. Now positron is the opposite of electron. Okay, see, in case of electron we express it as 0, 1, 0 e minus 1. But when we are talking about positron, it is the particle will be expressed as 0 plus 1 e. Now when positron is emitted, that is positive charge, now the atomic number of y that will decrease by minus 1. Again follow the same thing, plus 1, you add y minus 1, it will be y. That means left hand side, sorry, it will be z, not y. So left hand side it is z. Similarly, if we add 0, that is actually there is no mass, 0 plus a, that is also a. And the 5th one, now this process is basically electron capture. So you will see there is some difference in this, the last process, it is to some extent different. In the first 4 process, what we have seen, different types of particles are emitted. But now it will capture electron. That means the starting species X, it will capture electron, and the arrow should be here. So AZX, it is capturing electron, and as it is accepting this electron, now the atomic number will be y minus 1, because in the left hand side, sorry, it is Z. In the left hand side, if we consider the atomic that is charge, it is Z and minus 1 for positron. So in the right hand side, it should be Z minus 1, and that you can see here. Okay, and mass is A and 0. If we add A and 0, you will get A. So here mass is not changed, it is unchanged, but decreased by 1. That is after electron capture, it is decreased by 1. So see, the effect of positron emission and electron capture, these two are, that is final result is actually same. Okay, because here also A is unchanged, Z is decreased by 1. This is also A unchanged, Z is decreased by 1. Fine. So these are the different processes. So the name of these processes may be mentioned in the numerator. So that is why you should know it. Because when there is alpha decay, you have to remember that the new species that will be generated, that is Y in this case, it will have 4 mass decreased by 4, Z decreased by 2. Okay. So what is the final effect that we have to remember in each of these processes? Any doubt? Here we have a problem, 24296 cm. So see, this is having very high atomic number. There will be decay by alpha emission. That means alpha particle will be removed. Remember, in the last slide, the first process is actually mentioned in this numerical, that is alpha decay. Sometimes it may also be called alpha emission. And the final species that we are getting is Pu. Now in this picture, unshaded sphere represents Cm. That means this is Cm, unshaded. Shaded sphere is Pu. Okay. Question is, how many half-lives have passed in the following example? That means here we have to consider this reaction. Initially we have Cm where Z is 96, mass A is 242. Now when helium particle is removed, which is alpha, then we know when alpha is removed, 2, that is the amount which will be decreased from 96. So now the atomic number is 94, and mass will decrease by 4. So 96 minus 4, sorry, 242 minus 4, that will be 238. That is mentioned here. Okay. So initially the species is CM, which is this unshaded sphere, and PU is this shaded sphere. Clear? Now if we look at this picture, here we have total 4 CM and 12 PU. Now this 12 PU and 4 CM that you are seeing here, initially if we consider, there is only the unshaded sphere, right? That means initially you have only CM because CM is the starting material. So there will be 12 CM, that is 12 CM plus 4 CM. So this 12, from this 12 CM, basically 12 PU generated. So what we are doing, we are adding this number, and ultimately initially we can say there is 16 CM atoms, that is nuclei. Okay. Now half-life means what? 50% will be decreased. That means when it is fast half-life, the 50% of CM will be converted to PU. Now 50% of 16 is 8. So there will be 8 PU plus remaining 8 CM. Okay. Now the next half-life, second half-life. Now we already have 8 PU, which is the product side element, and 8 CM is still there. So the reaction that will be only from 8 CM. So now from 8 CM, what we will get? Again 50% consumption. That means now it will be 4 PU generation and 4 CM will be left. So now see, if you compare with this picture where we have already seen 4 CM left. Okay, that means here also we have 4 CM and total number of PU is 4 here already present and 8 here already produced. So you have to add these two. 8 plus 4, this is 12. So now it is matching with this picture. That means how many half-lives required? 2 half-lives. This is the first half-life. This is the second half. Okay. So the answer is, how many half-lives have passed? 2 half-lives. Is there any doubt? Is it fine? Next question. Radioactivity of a sample is mentioned as R1 when time is T1 and it is R2 when time is T2. If the half-life of the specimen is capital T, then the number of atoms that have disintegrated in this time interval, that will be proportional to which of these? Okay, so try to understand the question clearly. Radioactivity at two different time T1, T2, it is given R1, R2. Half-life is also given. So the number of atoms that will disintegrate in the time interval T2 minus T1, that is proportional to which of these options? Now when we are saying proportional to, that means it may be that A is equal to KB. That means if K is constant, A is basically proportional to B. Okay, so we have to find this type of relationship between, that is R1, sorry, T2 minus T1 in this time interval, the number of atoms that have disintegrated, that amount is proportional to which of these terms. Okay. Here we will consider lambda as the rate constant for this disintegration. Now we know that activity or radioactivity we can express in this by this formula. Sometimes activity is also mentioned by capital A. That is capital A, that is equal to rate constant or you can also call it as decay constant multiplied by number of nuclei. So this relationship we are applying here, and when it is R1 radioactivity, then decay constant will be same because it is constant, and N1 is the number of nuclei. N1 is the number of radioactive nuclei at time T1. Similarly, when it is R2, that is when the time is T2, we have another equation R2 equal to lambda N2. So just like here we have N1 is the number of radioactive nuclei, N2 is the number of radioactive nuclei at time T2. So now we have two equations. Okay, so what we will do, we can deduct one equation from the other. Fine. If we do so, that is subtracting equation 2 from 1, what we will get? R1 minus R2 left hand side, and in the right hand side you can take lambda common, which is decay constant, and N1 minus N2. So N1 minus N2, this will be now equal to R1 minus R2 divided by lambda. Now decay constant lambda, how it is related to half-life, because half-life is also mentioned. Okay, and we know that half-life you can write it as T half, that is equal to, for first order kinetics, because radioactive reactions are also following first order kinetics, the value is 0.693 divided by rate constant K. Now in this case it is basically K is lambda. So in place of lambda, now we can write that is equal to 0.693 divided by half-life, which is capital T, as it is mentioned in the question already, that is half-life is capital T, that is mentioned. So in place of lambda, now we will write 0.693 by T. So as lambda is in denominator, so finally the equation that we are getting is like this. Okay. Now in this expression, this part is basically constant, and R1 minus R2 into T, this part is variable. That means N1 minus N2, which is basically number of nuclei disintegrated. N1 minus N2, it is related to, that is, it is proportional to R1 minus R2 multiplied by T, because this part is constant. Okay, just compare with this equation that I have written here, as if here A is N1 minus N2, B is this part, and K is 1 by 0.693. So which option will be correct? Tell me. N1 minus N2 is proportional to R1 minus R2 into T. Which option is correct? Last one. Any doubt? Next problem. Here we have mixture of two different isotopes. Okay. Why we are calling it isotope? See here, Z number is not given, and here both the elements are same element, pu, but difference is only in the mass. One is 239, another one is 240. So isotope is where atomic number remains same, that is chemical nature, that is the element remains same, but mass number is different. Now mass number different means what? Their neutron number is different. So in first case, suppose one is having mass A, which is proton plus neutron, another is having mass A prime, which is also proton plus neutron. Now P is same, that means N must be different. So in the second case, N is prime. So this is the definition of isotope. Now these two isotopes of Pu, their specific activity. Remember specific activity, we have already discussed the definition. That is given. And look at the unit, it is disintegration per second per gram. Because when we say specific activity, it is basically per unit quantity. So that is why per gram. Now this plus per S, that means it is, you can also write it in this, dps per gram. Because this per second, that is nothing but dps. Half-life of the isotopes are given. So the first for 239 pu. The second one is for 240 pu. Look at the values. These are very high number and it is expressed in ER. So we have to be careful because here it is DPS, specific activity mentioned in DPS. That means per second. But it is here time half-life is given in unit of ER. So we have to do unit conversion, ER to second. Okay. Now what is actually asking in the question? Integer type question, isotopic composition we have to find out. That means if it is 100%, then what is the percentage of 239 pu and what is the percentage of 240 pu? That we have to find. Okay, because if there are 2 to 3 types of isotopes, for example, if we consider isotopes of oxygen, this is 16 isotope is there, then sorry, not 16, I mean to say that is, yes, it is 16, then 17, then 18. 3 types of isotopes are there and they have different types of percentage composition. We know 16 oxygen is the most common, okay, but there are other isotopes also. Similarly, hydrogen, another isotope is deuterium. Fine. So these are the different examples of isotopes. Now we will consider here 239 pu, its amount is X. That is X is the amount, X percentage you can say. So if it is X, then 24 pu, it will be 1 minus X. Okay. Now here 1 year we have to convert it to second. So when we are saying 1 year, it is 365 days. Now days, if you convert to hour, you have to multiply with 24. Then from hour, if you convert to minute, you have to multiply with 60. Then from minute to second, another 60. So ultimately, the value is 31536 10 to the power 3. Okay. Next, the equation that we will use is A equal to lambda n. Okay. For 239 pu, it will be N1. For 240 pu, it will be N2. Okay. Next, the calculation for 239 pu, the equation that we are using, A1, that is activity, lambda 1, that is the decay constant, into N1. N1 is the number of nuclei. Now here we have considered amount of pu is X gram and 240 pu is 1 minus X. Okay. Now mass is 239 and 240 and this is the mass. So what will be the number of moles for pu? It is N1 divided by X divided by 239. That is number of moles. For 239 pu, it will be given mass divided by molar mass. Okay. Now we know that in 1 mole there is Avogadro number of atoms. So if it is X divided by 239 mole, the number of atoms will be XNA divided by 239. So this is actually equal to N1. Fine. And how we will get the value of lambda 1? We know that half-life is given. And when half-life is given, you can easily find out the value of decay constant. So lambda 1 will be equal to 0.693 divided by half-life. Half-life is given here, which is 2.44 10 to the power 4. Okay. So 0.693, 2.44 10 to the power 4. But remember, this is in year. And if you want to do the conversion of unit from year to second, you have to multiply this value. 31536 into 10 to the power 3. Okay, so this is the value of lambda 1. So now we know what is lambda 1 and what is n1. Put the values here. Okay, so if you put it, you will see it is 9 into 10 to the power minus 13 for lambda 1, and for n1 the value is 2.52 10 to the power 21 x. Ultimately the value is 2.27 multiplied by 10 to the power 9 x. Okay, now what will be the unit? It is specific activity. A1 is specific activity, so the unit will be dps per gram, because x we have considered the unit is gram, or you can also write it as ds per second per gram, both are same. Or up to this point, is there any doubt? So just like 239 pu we have calculated specific activity, we will do the same for 240 pu. Okay, but equation will be changed. Now it will be A2 equal to lambda 2 n2. So same question, I am doing the second calculation in new slide. Okay, so for 240 pu, now I will write directly lambda 2, it will be 0.693 divided by, remember this is the half-life for 240 pu, so 6.58 10 to the power 3. Conversion from year to second 31536. I am following the same thing as we have done for other isotope. And in place of n2, what we will write? 1 minus x is the amount multiplied by Avogadro number divided by molar mass. Ultimately, the value that you will get. Remember, Na actually Na value is known to everyone, so that is why I am not writing it. But it is 6.023 10 to the power 23. And after final calculation, put the value of Avogadro number. It will be 8.38 10 to the power 9 1 minus x disintegration per second per gram. So now individually we know what is the value of A2 and A1. So we know the value of A2. We also know what is the value of A1. Okay. Now here the total specific activity that is given 6 into 10 to the power 9. So this is actually A, and A is equal to A1 plus A2. So total activity A equal to A1 plus A2. Now put the value of A1 and A2. Okay. So putting the value of A1 and A2, what you are getting? In the left hand side, we will write this value because this is A. Okay. And in place of A1, we will write 2.27 10 to the power 9 x plus A2 is, we have just calculated, both side unit is same, disintegration per second per gram. So from this equation you can get the value of x, and x will be equal to 0.389. so it means x, we know this is 239 pu, so this is the amount of 239 pu, 0.389, and total is 1 gram. So percentage of 239 pu will be 0.389 divided by 1 multiplied by 100. So this is 38.9. That means it is almost 39%. So if 239 pu is 39%, obviously percentage of 240 pu, it will be 100 minus 31, 61. You can also do the calculation in this way, that is, first you can subtract 0.389 from 1 and then you can do the calculation like this, but it will be less time consuming. So the percentage ultimately that we are getting, that because we have to calculate isotopic composition of this sample. So 39% is the amount of 239 pu and 240 pu, that is present 61%. So its percentage is high. It is around 40, it is around 60. Okay, so it is present in higher. So if it is asking what is the ratio, then the ratio will be 39 divided by 61. Okay, but here it is asking isotopic composition, so that's why we have expressed in percentage. Is there any doubt? Should I repeat? Because this is a that is, calculations are very elaborate. During nuclear explosion, one of the product is 90 strontium. Half-life 28.1 year. 1 microgram of 90 strontium was absorbed in the bones of newly born baby instead of calcium. Remember, calcium, strontium, both are from same group. That is, their chemical properties are quite similar. Alkaline earth metals. Okay. So instead of calcium, Sr is absorbed, that is strontium. How much of strontium, that is how much of each, that means how much of strontium will remain after 10 years and after 60 years, if it is not lost metabolically. That means by other metabolic processes, strontium is not lost. What it means? It means that whatever is the amount of strontium that is lost, that is only by nuclear explosion, not by any other method. Fine. Here half-life is given, that is 28.1 year. So if starting amount is x gram, after this year it will be x by 2 according to the definition of half-life. Okay. Now as half-life is given, we can calculate the value of decay constant. So k or lambda, whatever it is, 0.693 divided by t half. T half is 28.1. 0.0247 year inverse, because unit is time inverse, decay constant for first order kinetics. Okay. Now when it is 10 years, number one, what will happen after 10 years? So the equation that we are going to use, KT equal to 2.303. See, same equation that we use for first order reaction. So here initial amount that we will consider as if it is 1. Okay, and final amount is x microgram. Initial amount 1 microgram, final amount x microgram. Because in this relationship we take log initial amount divided by remaining amount. So that is why 1 by x. Now we have to find out what is amount remaining after 10 years. So basically we have to find out x. Okay, so log x by 1 by x, that is equal to 0.0247, that is the value of decay constant, multiplied by t. Here t is 10 year, right? This is year and this is year inverse, divided by 2.303, and this value is equal to 0.107. Now for log base is 10, so 1 by x will be equal to 10 to the power 0.107. That means x is equal to 1 divided by 10 to the power 0.107. After calculation, you will see the value is 0.782 Obviously the unit will be microgram. Though it is not mentioned in the question specifically how much of it will remain after 10 years, it is not mentioned whether you have to express in gram or kilogram or microgram. So you can do it in microgram. Okay. So this is for 10 years. And what will be for 16 years? Again, KT. Now this is actually T10. This is 60. 2.303 log. Now suppose the amount is Y gram. We will write the value of T, which is basically same. T is now 60. Zero 0.643 is the power of 10. So 1 by Y will be equal to 10 to the power. Sorry, this is 1 by Y. So Y will be equal to 1 divided by 10 to the power 0.643. Microgram. So this is the amount which is left after 60 years. So initially it was 1 microgram, and after 10 years, see 10 years is not even equal to half-life. It is almost 1/3 of half-life. Okay. So amount of initial, that is amount remaining after 10 years, it will be around 1/3, it is around 2/3 of the initial amount, and you can easily check it. 0.782, that means almost 2/3 of 1 microgram. Okay, so in this way you can check whether the final calculation that you have done, whether it is more, that is qualitatively it is correct calculation you have done or not. That you can easily check from these values. And the 60 year that you can see now, the amount is very less, 0.228. So compared to 1, this value is almost 1/5. Okay, and here half-life is around 30 years. So after 30 years, that is after first half-life, the amount of 1 microgram, it will be 0.5. And if there is another 30-year half-life, that is the second half-life, now it will be 50% of 0.5, which is almost 0.25. And see, the value is matching. Okay, is there any doubt? Should I repeat? Beta activity. Remember different processes we have discussed, alpha decay, beta decay. Okay, so this is one of that process. 1 gram of carbon which is made from green wood is 15.3 count per minute. Here the unit is in terms of count per minute, and this term is important. Green wood, that means it is fresh sample. So in fresh sample, the amount of carbon, what is its beta activity, that is given. And if the activity of 1 gram carbon derived from the wood of Egyptian mummy case. Now Egyptian mummy case, here the wood that is used, that is actually old wood. So that is the reason now the activity of carbon is decreased from 15.3 to 9.4 under the same condition. From this information you have to find out how old is the wood of mummy case. T half given. And T half given means you can easily calculate decay constant from this relationship. Lambda equal to 0.693 divided by T half. T half is given, you can easily find out lambda. And once you can calculate lambda, you have to use this equation. Lambda T 2.303 log initial amount, I am writing E, divided by remaining amount R. So here the reaction that is going on, that is beta activity of carbon means here carbon 14 6 carbon, though this equation is actually not necessary to solve this question, but I am discussing it because in case you are curious what is beta activity of carbon, then you can consider this equation. Here atomic number 6, mass number 14, and when there is one beta particle removed, that means nothing but removal of electron. Now it will change to another element which is N. Why it is changed to another element? Because atomic number is changed. Atomic number 6 means it is carbon. Atomic number 7 means it is nitrogen. Fine. So here, next calculation that we will do. So this is the relationship. Just put the value of T half 5770 years. You will get the value of decay constant. It may be K or it may be lambda, whatever it is. 1.20 10 to the power minus 4 inverse year. And ultimately we are using this equation. This equation, remember, it is KT equal to 2.303 log initial amount A naught, final amount remaining A. Put the value of A here that we have calculated, and initial amount you have to see. When it is normal chemical reaction, what we do, we put concentration value, but it is not chemical reaction, it is beta activity, it is radioactive reaction. So obviously initial amount it will be different, and as here unit is same, count per minute, count per minute. So when you are taking the ratio initial amount, and why, if you are thinking why we have written 9.4 is the in the remaining amount, the reason is when it is old wood, basically most of the carbon is now converted to N element. That means amount of carbon is now less. So the remaining amount of carbon for which the value is 9.4, that is why in place of remaining amount we have written 9.4. After calculation, as the unit of K is in year inverse, so obviously the T value that you will get, that is age of the wood of mummy case, that will also be in years. And if it is asking in the question that express it in terms of second or minute or days, accordingly you will do the unit conversion, but nothing is specifically mentioned. So it is 3920 years, that is the age of the wood of the mummy case. It is very old. Okay, so in this way, from this beta activity of carbon reaction, it is, you can say, one of the important application of beta activity of carbon, by applying which you can find the age of very old objects. Okay, is there any doubt? Any doubt? So we will end the session here, and regarding the whole class, if there is any doubt, you can tell me.
No,
Okay,
ma'am.
we are session here. Thank you for listening.